This AI4OPT seminar, so I'm going to play a little game, Jeopardy game, to introduce the speaker. So if I tell you that somebody is one of the 11 trailblazers identified by the Provision Journal, you're probably going to guess that they are from Brown University, as you can see. Okay, if I tell you that they get, that the person gets his or her PhD from UC San Diego, there is a very high probability that that person has a PhD in computer-aided design with some of our friends at the Philos Institute, right? So if I tell you that the person is an Amazon scholar, you probably guess that they work in supply chain. At this point, you're getting confused, right? If I tell you that the person is working on embedded system, on molecular computing, on energy efficient computers, you're getting more and more confused. You probably think that this person doesn't exist, right? And then you wonder why, we are here today. And then I tell you that that person works also on optimization and machine learning for optimization. And you definitely say, well, no, I really want this person to be invited at the seminar. And this is why we have Sharif today. Sharif is an IEEE fellow as well. He's a full professor at Brown University. We actually overlapped for 6 years, but I don't think we ever met there. That's the distance between the engineering and the computer science department, which is like one street. What else can I say about Sharif? I mean,
thank you so much.
Thank you.
Yeah, thank you so much. I appreciate it. I appreciate inviting me today and setting up the schedule and for this great introduction. I really appreciate it. So let's get into the topic, which many of you are familiar with, using machine learning for combinatorial optimization. And I'll look at some case studies in here from my lab and also from my experience in Amazon. So, of course, the general idea in here is that we had for 6 years very successful combinatorial optimization techniques. And the general idea, you're trying to find a combination or values for your decision variables in order to optimize for a certain objective subject to a certain constraint. And then in the last 20 years or so, we've seen the rise of machine learning algorithms. And not just in the machine learning algorithm, but also there has been a trend is that we're creating new hardware, the GPUs, and platforms like CUDA that enables you to use it for general purpose applications, and then frameworks built on top of that like PyTorch. So this machine learning is not just a revolution in terms of algorithms. There's also an underlying hardware revolution going with it, and that allows us to get much more speed ups when we run these machine learning algorithms. And the traditional input to those has been images and sounds. So there's this kind of like people might think, oh, it's disconnected from combinatorial optimization. How can I use these algorithms for combinatorial optimization? And the question is really, why do we need to do this? Like, what's wrong with combinatorial optimizations? And you really have two main deficiencies on combinatorial optimization, which is one of them, you end up solving the same problem instances from the same distribution on a daily basis, and you're not learning anything to improve the quality of results or improve your runtime. And this is particularly important for industrial context. When you are working in academia, you're probably solving a different problem every day. You actually don't have the problem or the data to the problem. But in industry, say you're working in transportation planning, you're solving the same problem every day. Just the coefficients have slightly different values. The right-hand sides have slightly different variables, but it's kind of the same problem. And every day you generate a solution, and then you never use the solution afterwards like to learn anything useful to improve the quality or the runtime. And also combinatorial optimizations could be notoriously solvers. You're after all solving an NP-hard problem. So you could be very slow and you could be taking a lot of memory in order to solve it. So that is really the problem in current combinatorial optimization. And that's where lies the promise for machine learning. The promise for machine learning is that, hey, I'm solving these problems on a daily basis. Can I use all the solutions that I've got in the past in order to improve the quality of results or runtime going forward? And not just that, I can leverage all these machine learning algorithms to train from the past. And I also have all these additional computational platforms. Why am I stuck doing some branch and bound on a CPU when I can run things massively parallel on a GPU? So that's where the promise of machine learning for optimization is. Hopefully we get improved scalability and or improvements in the quality of results, especially when your combinatorial optimization solver have time constraints. Obviously, if you don't have time constraints on it and you let it run, who knows, maybe for years or days to get your optimal solution, you cannot beat that. But usually, you would impose a time limit on your combinatorial optimization solver. All right, so if you look at the landscape of machine learning for optimization, and like you guys have, I've been talking with you, so each one of you can start to think, where am I exactly falling on this landscape? You will see three main directions, or I try to bucket them into three directions. The first one is that you're running your machine learning pipeline before your combinatorial optimization solver. So you're still using your optimization solver, but you're running a machine learning pipeline ahead of it. Why is that? Because I might need this machine learning algorithm to predict for me the values for the coefficients or the right-hand side in my optimization variable. And this arises especially in planning. I'll show you examples on that. Or I might run a machine learning algorithm in order to configure the hyperparameter for the combinatorial optimization algorithm. That's something also I will show you today. In another approach, you say, you know, why should I do that? Let me just substitute my combinatorial optimization with a machine learning algorithm directly. And a lot of you are also working in that area. So in that case, you either trained on the past or your training algorithm itself will find a solution kind of like as if it's a surrogate function. And in that case, your substitution, the optimization, and there's a chance you might have to clean up or repair your solution from the machine learning algorithm. The third direction is that the machine learning algorithm is working in tandem with the optimization. So in here, you have your typical optimization solver, but it's an iterative process. And as with each iteration goes, it's using the machine learning as kind of its helping hand. It's helping it decide on some of the choices it might face as the algorithm unfolds. So this is, I think, is the three broadest categories for classifying the machine learning for optimization research. I'll look at some case studies from transportation logistic planning. From my experience, I'm not going to be able to share numbers in here for confidentiality, but I'll be able to share some of the insights and challenges in that area. We also done work academically in my lab, so we can go into a little bit more in depth with numbers like in integer linear programming solvers and optimization for digital circuits. So let's go with the first one, which is I'm using the machine learning to help me before I run the combinatorial optimization. And like I said, in here, the first thing you can do is you can actually run this machine learning pipeline to actually generate the model. So your optimization problem, it's solving some ILP, but all the coefficients, potentially most of these coefficients on the right-hand side values are actually coming from your machine learning pipeline. And this is the most difficult thing I've encountered in industry. That is the most common thing you can do. And I'll show you why would this happen. The other thing is that this machine learning model can make some partial a priori decisions. There could be some decision variables, for instance, that your machine learning model will say, you know, this decision variable will be 0. It's been always very small. I'll just set it up to 0. Or it's been always 10 or very close to 10. I will set it up on 10. So it's not solving the whole problem, but it's breaking down the problem, right? It's setting the values for some variables so the problem becomes more scalable. Maybe you're lucky and you can decide on some variables to actually even partition the whole problem into pieces, and then you can solve it in parallel. So this is one approach. So let's look at one example. And of course, in all of these things, you're getting speedups. And the first one, you wouldn't have been able to solve the problem. So let's look at an example for the first case, which I think is the most common case I've encountered. Let's take on logistics planning. Let's say you have some zip codes in here. Very simple case. You have zip codes. Each one of these zip codes have a demand. They're going to make certain amount of orders. And you have warehouses, and you actually have your own fleet. You have your own trucks that will deliver from these warehouses to the customer, all right? And each warehouse has a certain mechanical capacity. It has a certain inventory snapshot of the different products that the customer might order. Very classical problem. And in here in logistic planning, I want to procure resources in advance to make that delivery happen for people when they place their order. So I want to be able to know, say, next week, how many guys should I hire at the warehouses? How many trucks should I have in order to be able to deliver on these orders when they come? So you really want to procure resources in advance. That's the ultimate goal of solving this problem. So this is an easy problem, relatively speaking, in terms of conceptually. You have demand at zip codes, you have inventory at warehouses, you have mechanical capacities, you have distance or cost for transportation from the warehouses. So you can imagine writing a nice ILP, right, with a certain objective function, minimize total distance, subject to inventory constraints, subject to mechanical constraints, subject to meeting the demand. And once you solve this, you get these values, you get those numbers on the arrows. Those numbers says, you know, I'm going to deliver 7K to the zip code, 7K packages or orders from that warehouse. And I'm going to deliver another 3K or orders from the second warehouse, and so forth. So this is basically the outcome from that solution. And then you aggregate, you say, okay, I have 7 plus 16, it's 23 plus 2, 25. I have 25,000 orders coming to that warehouse. I need to hire 1,000 labor. I need to have 15 trucks going out of that warehouse to this different zip code. So that's going to be the outcome of your decision making in here. But there is a whole caveat in here. The caveat is that if customers are placing these orders, hiring decisions are not made on a second, right? I have to make these hires well in advance before this demand actually materializes. So this means I have to solve this problem today to secure the resources for next week's demand, right? I'm not going to be able to hire labor. I'm going to call somebody today or show up tomorrow at work, right? I need to at least to tell them 1 week in advance, and the same thing for trucks. So this means that I need lead time, and this means that I'm solving a combinatorial optimization now to procure resources for next week's delivery needs. So what does this mean? Well, it's a problem a little bit, because if you look at the previous problem, I was putting demand in here, the demand is known, and the inventory snapshot is known. Yeah, that's if I solve it now, but if I solve it 1 week or 2 weeks from now, all of these values have to be forecasted somehow. So that's why you're going to see in industry, in many cases, a machine learning pipeline feeding into the solver that you're going to use for the combinatorial optimization. And that machine learning pipeline is essentially forecasting all these coefficients on the right-hand side values that you typically encounter in your optimization formulation. I need to forecast the demand. I need to forecast the inventory snapshot. Maybe I need to forecast fuel costs for transportation. Even the time taken between different origin and destination point, I might have to forecast them. Next week might be different than this week. Saturday is different than Wednesday, and so forth. So in that case, you need this machine learning pipeline. And like I said, maybe you would look at the previous results and see, oh, you know what, this warehouse never delivers to the zip code. I don't need to make it part of my optimization. I will always set it at 0. Now, this makes it very interesting, because the final quality of results from your optimization problem is as good as your machine learning algorithm. That's essentially what it is, because you're deciding how many packages are going to be between every warehouse and destination. And the only kind of thing that can throw off your optimization solver is the quality of your machine learning. If my forecasting algorithm is 20% error, then basically my combinatorial optimization results will be a pretty bad mess. Garbage in, garbage out at that point, right? So you still have your optimization, you're thinking you're optimal, but it's really garbage in that you're using. So that's why I'm saying the quality of result is as good as the machine learning quality. So what are the challenges in that paradigm? What can throw me off, or what would you actually see as a challenge? Forecasting accuracy. If I'm forecasting demand at a zip5 level granularity, which is a very fine granularity, you could have inaccuracies in that demand, especially when you have special events. Maybe daily to daily, it's fine. But you know, how much will I ship in next Cyber Monday, Black Friday? You know, all of these high volume events are sometimes much harder to predict, because you don't have enough sufficient training data. Your training data is based on typical daily to daily demand. Then you go to these high volume events, and suddenly your forecasting is down. And guess what? That's actually where you need the optimization results the most. Because you know, if you have a lot of demand and you don't have resources on the ground that you procured in advance, people will get the deliveries late. So that's a big problem. That's a big challenge. Second thing is the data amount and the training that you will need to run this machine learning pipeline. So this particular problem, for instance, if you have roughly 42,000 zip codes in the United States, if you have a network that has tens or hundreds of warehouses, then you're talking about a huge combinatorial problem that you need to solve. It's going to take hours and hours. Now I'm adding to this runtime, the runtime of a machine learning pipeline that has to figure out for me all the values and the coefficients on the right-hand side of my optimization. So that's going to add a huge amount of runtime. How often should I train it? You know, runtime challenges. So all of these things actually are typically scheduled, meaning that we're scheduling at 8 a.m. the machine learning to run. It has to finish by a certain time so that the optimization starts running at 11 a.m. So you actually have a tight time window to get the results before you can run your optimization. Sometimes new warehouses pop up, or even zip codes. Believe it or not, zip codes are not static. The zip5 codes are not static. They can actually grow, and there's new zip codes all the time. So in that case, if you get a new warehouse or a new zip code, how can I forecast the inventory snapshot in this warehouse when I don't have any historic data? How can I forecast the demand in that zip code or even the boundaries change. This area was part of that zip code, changes to that zip code. So you might not have any data so that you can actually forecast the right values for your optimization problem. So that's another challenge. What we call bridging or explainability for quality of result loss after execution. So this is actually interesting. So let's say, for instance, I run the optimization based on my forecast, and I predict that I need 10 trucks between a warehouse over there and this zip code. Good. We come to execution day, and based on the demand of that day and inventory snapshot, I end up using actually 7 trucks out of the 10. All right. So it's a business decision. You hire, you procure 10 trucks, use 7. Tell me why you didn't use the 3. What happened so that you didn't get the 3? How are you going to go about that? So that's what we call bridging or explainability. And it's a problem, because in that case, I need to run my optimization algorithm again using the actual data. So let me use the actual inventory snapshot, but the forecasted demand. I see, oh, you know what? It actually looks like I need 8 trucks if I use the true inventory forecast. If you use the true demand, but the forecasted inventory, then, oh, I need 9 trucks. And then, of course, all of these things are combining. All of these variables that it's not a linear. So you cannot say, oh, I lost 1 truck because of demand forecast. I lost 2 trucks because of inventory. I lost 3 trucks because of cost fuel. You know, those errors are not adding up linearly in your combinatorial optimization formulation. They also can interact non-linearly. So after the execution happened on that day, we need to explain why we said 7. We said 10 and it came out at 7. So I have to run my combinatorial optimization problem again under all these various scenario or combination of actual versus forecast. I'm trying to build a bridge to say, you know what, we said 10, it came out at 7, and we lost 3 trucks, and we think 1 of them is because of demand forecast, 2 of them because of X, Y, and Z. So this also adds up a lot of complexity, because now I have to run my combinatorial optimization under all these various combination of forecast versus actual to build that bridge or explainability at the end of the day. So that's another challenge we typically face, because if your combinatorial optimization takes 5 hours and I need to explain the results, what happened for this discrepancy, this might add a lot of runtime afterwards. So this is the main challenge in here. Here's another approach also for using ML to set up combinatorial optimization. In here, you can set up a problem, and you can also control the hyperparameters for your combinatorial optimization algorithm. And oops. Okay, so this is one thing. Like, you know, I will show you an example on ILP solvers from my lab. You can also have a repertoire of combinatorial optimization techniques. Maybe you have some meta-heuristics or heuristics, and they don't dominate each other. For some instances, this algorithm works well. For some other instance, this algorithm works well. So they are not dominating. So in here, your machine learning algorithm can say, look at the problem instance and you're receiving, and say, you know what, for these kind of features in my problem instance, I'm going to pick algorithm 1. You get another instance, and it says, for these features, I'm going to pick algorithm 2. So in here, that would be kind of like the maestro that select which algorithm to run from the repertoire of your optimization algorithms. So let's dive deep a little bit into this idea that I can run the machine learning to set up the configuration parameters. So this is in here from my lab at Brown, based on a recent paper we published in the Annals of Operations Research recently. And the idea is that any ILP solver, if you have used of them, they usually have tens, if not hundreds, of configuration parameters that control the quality of solution and runtime of your solver. Typically, you would have an optimization problem. It's hard to solve. It's going to take days or maybe even forever to solve. So you have to give your solver a runtime limit, okay? So for instance, this is one of the ILP instances we have. You give the solver 15 minutes to solve it. And then depending on which configuration you choose for these parameters, you get totally different final results, okay? So definitely the configuration parameter you use for the ILP solver has a big impact on the cost you finally get. So the question is there a particular global configuration that is good for all instances? And the answer is no. We have data for that, and everybody knows that. So this means that every problem instance or distribution can have its own special configuration that is particularly optimized for it. So I need to figure out for each ILP instance, what is the best configuration that minimizes the cost. If you look at the previous algorithms there is like hyperparameter searching algorithms, like Bayesian searching algorithm that tries to find a good configuration that works on a distribution of instances. And also another technique, which I will describe today, that's going to be similar to what we're doing, is that I get a new problem instance. I've already solved offline a few problem instances in the past, and I figured out the best configuration for each one of them. I get a new problem instance, and then I say, okay, this problem instance is similar to this one that I solved in the past. And this one that I solved in the past had these best parameter configurations. So I'll take these parameter configurations and apply it to my solver. So in that case, you used all what you've learned about in the past, about what are the best settings. A new instance comes, you measure the similarity to previous instances, and then you pick the configuration and you apply it. This is kind of the general flow. I'll describe really that secret in here, or the hard part is similarity. How can I say the two problems are similar? In the past, the way people define similarity, they say this problem is similar to this one because it has the same number of decision variables, it has the same number of constraints. If you compare the coefficients numerically, say using a Euclidean metric space, it's very close to it. The right-hand side constraints are very similar, numerically speaking. So as a result, I think those two problems are similar. However, that is not, we think, is the best way to do it. And I will show you by results that that is not the case. So what is our hypothesis? Our hypothesis is that we're thinking that if two instances trend together in terms of how the configuration impact their solution quality, I will define them as similar. Meaning that I apply the same configuration for my MLP solver, and I have two instances. If I see that their costs are trending with each other, quote unquote correlated, it's not linear or anything. But if they are trending with each other, meaning that for this configuration, it reduces the cost for both of them or increases the cost for both of them, then in that case, we say those two problems are similar. They are similar from the perspective of the configuration that I care about. So this means that if I find a configuration that minimizes one of them, it's very likely that it will minimize the other one, because I know that the two configurations are trending with the two instances are trending with each other under the same configuration. Okay, so this looks like it's intuitively makes sense. But the caveat in here is to figure if two instances are trending with each other is to actually solve it. I need to solve it, but that defies the purpose. I need to actually have a very quick way. I need to learn some kind of a features that can extract from the two instances and say, hey, look, given those features, I think those two instances will trend with each other. That's the idea in here. So not in here, we actually want to learn the features. We want to figure out what is the right features that we should look at to say those two instances will trend with each other under the same configuration. So this is what we're proposing in here using metric learning. So it's the Milk-Tune approach. That's the focus of this paper. And the core idea is this metric learning at the end. So the overall flow looks like this. This is part of it is standard flow right now in the literature. The novel part is the last piece of it. The first thing is that you're gonna have some, of course, training instances of ILP instances. You're gonna solve them, you're gonna get the cost. And then once you get the cost under the different configuration, you can tell which instances in your training set trend with each other, which ones are similar, and which ones are not similar. Okay, so that's the first thing. So we can know that information. Then I want to create a machine learning pipeline that can tell me this information in advance for test instances, for instances that I have not trained. Okay, so the general idea is that I'm going to take my ILP represented as a graph, as a bipartite graph in particular. I'll show you how this works. And then after I represent it as a bipartite graph, I'm going to run graph convolution network. The outcome of this graph convolution network is an embedding, is a vector, is a tensor at the end of the day. That represents my ILP instance. Now that tensor, afterwards, I will run something on it called metric learning. In metric learning, I'm trying to transform these vectors such that if two problem instances trend together under the same configuration, they will move close to each other. So this black and green, they were originally far from each other. I applied this metric learning, so it rotated all the points such that the two instances that trend together under different configurations become close to each other. Those guys actually have the same cost as up and down as you change the configuration. And the two instances that actually have this similar cost as you change the configuration end up being far from each other. So the end point is that I want to rotate these embeddings, transform them such that problems that are similar under this idea that I mentioned to you become close to each other, and problem instances that are not similar to each other move from each other. So that's the metric learning. So it's like a function. I'm trying to learn a function that separate instances or give me a very high cost for instances that are not close to each other under this idea. If I have two instances that trend like this, my metric function should give me a very small cost. But if they are not trending with each other, my metric function should give me a very high cost. So let's look at a little bit of the details. So this is also called triplet sampling, this idea, if you're aware of it. When you have your training data set, you want to pick a sample of 3 instances. Your anchor, one in problem instance, another problem instance that is very similar to it, that's the green dot, and then another problem that is very dissimilar from it, using that notion that I described in the previous slide. So that's a triplet sampling. And then you learn this metric function at the end of the day that's trying to bring similar instances close to each other and dissimilar ones far from each other. All right. Okay, so the first step is to represent your ILP as a graph. If you don't know how to do that, this is a standard idea in the literature that was proposed a few years ago. You're going to create a bipartite graph. One set of nodes, the ones on the top, corresponds to your variables. And then the sets of the nodes at the bottom corresponds to your constraints. You have an edge between a node and a constraint if it participates in that constraint. And then you have labels that correspond, say, to the cost. C1 in here is your coefficient and the objective function. And the different coefficients that in the constraints belong as also weights your edges and so forth. So this is a first standard step to translate an ILP into a graph. And then once I have this graph, I need to create an embedding for it. I need to essentially summarize it by a vector that I will then use in my machine learning pipeline. So in that case, we use graph convolution networks. There are certain features, of course, you can extract for the nodes in here, like the binary, continuous, integer, the lower upper bounds, the constraint type. These are all becomes part of your initial features for each node in your bipartite graph. You run your GCN, and then at the end of the day, you're going to have a vector, the embedding vector for each node in that bipartite graph. And in our case, we just average all of those at the end. So at the end of the day, it's just a vector of 256 number that represents really a feature or the embedding for this graph or this ILP instance. So that's how we translate an ILP model into a vector at the end of the day. We go in here. Then the next step is that, okay, I have those 2 embedding for 2 instances like X and Y, and I'm trying to learn this metric learning. I'm trying to find this matrix W that's going to do this transformation for me such that if 2 instances are close to each other under this notion of the configuration, they become close to each other in the metric space, and if they're far away, they become far away. So if I take, for instance, this is one of our instances in here, our ILP family distribution of all the instances in this problem, and then we run them through the graph convolution network, we get the embedding. It's a vector of 256 entries. And then I'm going to plot them in 2D using t-SNE, the t-SNE algorithm that basically going to project them down in 2D. And the color of each instance in here, each ILP, is its cost. So you will see in here, if I solve all of these instances and plot them, you can see some dots have high cost next to low cost. It's pretty mixed. It's all over the place. When we do the training and figure out this metric learning, this transformation, we transform all these instances into the new space, the metric space. And you can see that in this new space, instances that actually have similar costs, which will trend with each other in the configuration space, they actually become close to each other. And then all the instances in here that actually have similar costs, also low costs, are actually trending in that space. So you can see like a reorganization of that space, a transformation such that problem instance that are trending together under different configurations become close to each other in that metric space, okay? So this is the kind of final training pipeline. Like I said, you have a lot of problem instance that you're going to solve with your combinatorial optimization solver, your ILP. You get the costs into a different configuration. Then you're going to pick 3 triplet samples, one anchor problem, another problem that is similar to it when you change the configuration, another one that is not similar to it when you change to the configuration. You're going to represent all of these as graphs, bipartite graphs. You run the GCN, that's going to generate a vector, the latent vector embedding. Then you run it through the metric learning to transform these vectors. And then in here, you want to find the weights for your metric learning. You want to find the weights for your GCN such that if the 2 problem instances are similar to each other, that's the loss function. You want to minimize the distance between them while maximizing the distance between the anchor instance and the negative one, the one that is dissimilar to it. So I'm trying to find out the right weights for everything such that I bring problems that are similar close to each other and problems that are dissimilar to each other under this notion of configuration away from each other. All right. For instance, this is ILP problems from the ML for combinatorial optimization competition. They have 3 benchmarks: item placement and load balancing, scheduling problems from Google cluster. And then there was an anonymous problem that was also given for that competition. You can see that this is the t-SNE embedding of the original problem instances. This is the solution of the primal. That's the value for your cost function in here. And you can see how points with different colors are just scattered all over the place. Once you run this machine learning pipeline, you can see that your training data is kind of realigned in this new metric space, and problem instances that are similar to each other under the cost objective and different configurations is actually clustered. You can see a little bit more clustering in that space in here and in here. So you can see that visually it's actually working. It's realigning the embedding of the problem instances under that notion. Let's look at, and during runtime, it's very easy now because you're going to take your problem instance, you're going to represent it as a bipartite graph, you run your GCN, you get an embedding, you take that embedding, you multiply it by the metric learning matrix, you get the embedding in the metric space, and then you continue as usual. You find in your training set problem instances that have embeddings very close to it using key nearest neighbor, and then you pick up the configuration, the best configuration, and you apply it to your solver. So it's very fast during inference. Let's look at some results quickly. So again, these are 3 problem instances from that competition: item placement, load balancing, anonymous. We're using the skip solver. That's our MILP solver. We're given a runtime of 15. And then we have 100 test instances for item placement, 100 in load balancing, and 20 in anonymous. Okay. So the question is, we want to compare different methods. And basically, we're going to solve each one of these instances in my test set with all of these different methods and see how many times it wins. Which one, like, if for instance, in this case, default skip configuration, it only wins 1 case out of 100. Out of the 100 instances, that skip configuration gave me the best result. It lost in the other 99, meaning the other techniques found a better configuration than it. This is SMAC. It's a very popular search algorithm, hyperparameter optimization. I'm sure some of the people here in the room have used it. It only wins in 8 of the 100. Hydra, also another very popular, to use random forest to figure out the configuration. It only wins 10. Shallow embedding plus KNN. Shallow embedding is this idea that I mentioned earlier, that you base your similarity based on, how many decision variables I have, are the coefficient numerically close or not. Very, very simple way to do the embedding, but only wins in the 16. Our approach, which uses the deep metric embedding plus the k nearest neighbor, wins in 65 of the cases in here, 40 here, and 4 out of the 20 there. And also you can ask, when it wins, by how much? Is it like a small win or a big win? So in this case, for instance, it wins in 65% of the cases, and the average improvement in the cost function is 38%. So we're not just winning in more instances, but we're also winning by a big margin in that case. Any questions on that part or the previous part before I move on?
So when you train, how many configurations do you look at for every one of the instances?
Like in the
data set originally.
Yeah, like in here, for instance.
Yeah, exactly. So
you can actually do it even as less, if just one of them. We actually found that you can even just do it good with one. Like if I see when they're trending and I pick one configuration, what happens? The 2 costs are actually very similar to each other. So even just one configuration can be good enough. If I run one configuration on 2 problem instances and I see the solution is very close to each other, then there's very likely chance that they will be trending with each other. So you can do it with just one configuration.
Random one, or you do it?
You can pick a random one. Yeah, random one. So we tried that, and yeah, it's as easy as that. Any questions? Go ahead.
Does the president need to retraining the model for each separate task?
Yes, so excellent question, and that's the general problem with this machine learning for optimization, which I will talk about in more details, that each one of those has been trained separately. You're not generalizing. It's not like I trained in here, right, and I learned something and I move it to in there. Each one of them is on its own separate. That's because each one of them, again, has like different decision variables. It's like a different distribution altogether. Any other questions? Go ahead.
So So how do you plot the distance? So if you go back to one slide, so there is a plot showing the clustering behavior in the two-dimensional space.
Yeah.
So, but I assume the parameters are very high dimensional.
Yeah, so you do t-SNE.
How do you-
T-SNE, you use T-SNE algorithm, right? Because it's a 256 vector, you want to plot in 2D, so use t-SNE, and that's how we get the plot. It's a good visual way to actually show people that it's working. Any other questions? Alrighty. The next one is to actually substitute the optimization algorithm altogether with a machine learning algorithm. And I've talked with some of you earlier today, and I've seen this happening in a lot of cases. And also when Pascal gave a talk at Brown, I think many of his examples belong to this. So I'm running out of time. I'll see which ones to pick. Okay, so why would we actually do this? In the other case, it was actually essential. I need to forecast all the values to solve a problem about the future. The machine learning was not a yes or no. It wasn't an option. I didn't have any luxury. I have to run it. In here, why would I run the machine learning algorithm? What's wrong with the combinatorial optimization? And again, the problem is the runtime. Okay, maybe you want to solve a problem and you want to solve it online in a very fast fashion. You want to have a tight latency requirement, and you cannot get it with the combinatorial optimization. So you say, what? I'm going to run a machine learning algorithm that's been trained on past data, and that's going to give me the solution much faster. Now, there's always a risk that that solution has problems in it. Maybe it has some feasibility problems. Some of the constraints are violated, or maybe you wanted integer solution is giving you fractional. So you have to do some solution repair afterwards. And of course, once you, if you can cast your problem as a machine learning model, you can build your computational graph, say with PyTorch, run it on the GPU, get huge accelerations in the process, and that's how you can solve this for online systems. So this is one way to go about it. There is usually multiple approaches in here, but the main challenge really is that if you're going to build a machine learning model to approximate your, or to try to mimic your combinatorial optimization, the most of the challenge really is in the loss function. Because when you are doing regular machine learning, your loss function is differentiable, right? It's convex optimization. You can run your numerical solver, Adam algorithm to figure out the weights. But there is nothing that says your combinatorial optimization will have this differentiable function. It's most likely doesn't have that differentiable function. So in that case, you're trying to approximate it by some loss function, and that's really where a lot of the research is. What it would be a good loss function to kind of get me the behavior that I expect when I run the combinatorial optimization, or sorry, when I run the machine learning. A major challenge in here is really the loss of feasibility. There is nothing that guarantees that your machine learning algorithm will respect the constraints in the problem, or say that the variables have to be integer, for instance. So in that case, you're going to need to repair it. And that repair will likely cost you some loss in quality of results. I'll talk about this. It's a major challenge, but this is one big one. But maybe some people who argue would say, you know what, with a time limit anyway, maybe my combinatorial optimization wouldn't have been optimal. So this loss of quality of result is acceptable anyway. You also need a ton of training data to figure this out. Robustness is a big challenge also in this area. I want to actually speed up a little bit in here. Let me talk about this one. This same logistic planning that I mentioned, this inventory to warehouses. How can I recast this to an actual machine learning approach? So some people might think, oh, you know, I have the combinatorial, the ILP, I'm going to build a neural network to solve it. But there is even easier ways to do it than that. Let's think I've been solving this problem for the last 60 days. What is the final outcome of those solutions? The outcome is that I have a vector that has 6 entries that tells me how many orders are going to be assigned from each zip code to each warehouse. It's a vector of 6 numbers. Obviously, it's much bigger than that in reality, but it's a vector. And I've been seeing that vector for the last 60 days. Can I treat this problem as a forecasting problem? All I want to do is to take those 6 values and forecast their value for tomorrow. So I can actually not even try to, you know, solve the optimization with a surrogate machine learning model. I'm just recasting the problem altogether to be a forecasting problem. Once you recast it as a forecasting problem, you have a ton of machine learning algorithm to use, vector autoregressive, ARMAs, XGBoost, Profit, ton of things you can use to forecast the value for next day. And once you forecast this value base, I see a waveform. This is how many packages I got in the last 60 days. This is the value that I get tomorrow based on this. So those last 60 days, I solved them with the combinatorial optimization, and that's where my training data is. So I'm using the values from all the optimization I've done in the last 60 days to forecast tomorrow's. So that's it. I can solve it as simple as that with machine learning. But you can get into violations because it's just the approximation is done through the forecasting algorithm. Let's say, for instance, let's look at one real way to repair it. Let's say my forecasting algorithm says for tomorrow, it's 7 units or 7 orders between this demand code and warehouse, 20 here and 4. You can immediately see the violation, right? If I add those values up, they will come up to 31K. That's above the mechanical capacity for that warehouse. So what would be an easy way to repair it? Simply convert it to fractions. This becomes 7 over 31, 20 over 31, 4 over 31, and then I multiply those fractions by 30. So that automatically renormalize my numbers so that they meet the constraint. So this is very one easy way to repair your solution, machine learning solution, and you got your results very fast. And I don't need to run any combinatorial optimization anymore. I run it for 60 days. That's good enough. There is some lot of work that people, for instance, say, I'll take that solution. This is obviously a heuristic to repair it. Maybe somebody else, you know what, I'm going to write a sort of a mini combinatorial optimization problem that is much less complex, just to perturb things gently here and there in order to meet the constraints. That's a valid thing. You could do it. If you think this new combinatorial optimization is much easier than the original one. Robustness, which I will talk about. I need to get to that because I think the challenges are very important in here. But robustness, to very quick, if I shut one of these lanes tomorrow, or if I add a new warehouse or like a zip code split, this forecasting algorithm now will be very miserable, right? So this machine learning model infrastructure that I built will not work as good anymore. All right, we have this ongoing study, for instance, on the MaxSat solver that tries to build this kind of surrogate function. It tries to build a deep neural network and a loss function in order to replicate what a combinatorial optimization would do. I'm not going to go through details very quickly, but if you have a Boolean satisfiability, you have a formula, a Boolean formula, you want to see if it's satisfiable or not. If the formula is unsatisfiable, then you might ask how many clauses can I satisfy? So you want to try to maximize the number of satisfiable clauses in here. So again, the idea is that you have this formula, you're going to run your MaxSat solver with a branch and bound. That's the combinatorial optimization approach. But you can say, I'm going to build a neural network that mimics the structure of my MaxSat formula. Then I will try to find a nice loss function that I can then minimize. And in the process, I try to maximize the number of clauses I will satisfy. So I don't want to go through the details, but you can build a neural network that does that. And in that case, the weights of the network that you are going to identify through the training are the actual values, eventually will become the actual true or false values for your Boolean variables. So in here, you don't need any training data. But when you get a new instance, you're going to build a graph, a computational graph. And in the process of trying to minimize the loss, you're going to figure out the weights. And the weights in here becomes the actual values for your Boolean variables. So in here, for instance, the Boolean variables are going to be true or false. So you relax it, you make it continuous. And in our case, if the variable ends up being positive, we assign it true. If it's negative, we assign it false. And then you're going to have a hidden layer that combines those variables depending on how they look like in the clause. So if a variable, say a literal that says X, it has a coefficient of 1. This is a colon for each one of the clauses. And then if a variable, say X, there's a coefficient of 1. If it's Y bar, then you have a coefficient of -1. That's how it looks like. This, for instance, here's a formula. That's how it would look like. You can see I have a column for each clause. This is -1 because it's X1 bar. This is -1 because X2 bar. I have 1, 1 because it's X1 and X2. And your loss function is basically trying to minimize all the negative scores at the end of the day, because all of the negative scores indicate that this clause has not been satisfied. So if you're trying to minimize the negative values, then you basically, you're trying to minimize the number of unsatisfied clauses. It is still work in progress, but we do actually have encouraging results. This is one of the Boolean formulas we're trying to solve. Torch MSAT is our approach. These are other 3 state-of-the-art combinatorial optimization solvers. In here, we're plotting the number of unsatisfied clauses. So the less, the better, okay? And this is the problem instance size. So you can see as the problem instance sizes grows, our algorithm is scalable, this red line, and it's comparable with the state of the art. But this is still ongoing work because we have other instances that doesn't work as well. I'm just not showing them, all right? But it's an ongoing work. But this is the general idea. I want to give you just the general idea without the details. I have 10 minutes left and I want to leave some room for questions, but very quickly, this one I'm not going to go using reinforcement learning. So we also done some work on reinforcement learning. So you can remove your optimization solver, replace it with a machine learning solver that uses reinforcement learning. Okay, this is also a very popular research direction. In here, we applied it for the case of circuit design. When you're designing circuit, the problem is that you want to have a circuit that meets the functionality, that gives the functionality that you want, but also you want to have it with the minimum area. You want to use the minimum amount of area because that means cost. You also want to meet timing requirements. Okay, so it's an interesting problem because again, there's an objective. I want to minimize area subject to I meet the timing constraint. I want my design delay to be no more than 1 nanosecond, for instance. It's a classical NP-hard problem. Not going to go through the approach in here, unfortunately. I'm talking maybe slower or talking more than I expected, but I will skip that because I want to get to the challenges. Okay, the third approach. So we talked about the first two. The third one is you use machine learning as in the loop with your optimization solver. Okay, so just to give you very quick examples of some of the things in the literature, let's say you're doing a branch and bound algorithm and you want to pick your next variable to branch on, right? So which one should I use? Well, I can use a machine learning algorithm to say, given this problem instance and given how things unfolded so far, I should pick this decision variable, okay? Or for instance, maybe this hyperparameter tuning, maybe it doesn't need to be done once at the beginning. Maybe as you're solving the problem, and as things are unfolding, you can change your mind and say, given what I've seen so far, I'm going to change my hyperparameter. So again, this is kind of an in-the-loop process. So there's a number of examples in here, but I want to allocate the last maybe 5 minutes to the challenges, okay? All right, the first challenge, I think, is the most important in this area is robustness. Robustness meaning what? Some people call it generalization or make it the model generalizable, but I think that's a solution. I think the real problem is that the challenge is that you need to be robust. If I have a machine learning algorithm that is feeding into an optimization problem or substituting the optimization problem, I don't want it to be tuned to the point that if a new problem instance come out of a little bit of the existing distribution, I'm doomed. It doesn't work anymore. Why? If you are working in a business context, you don't want to be firefighting every day. You want to have a reliable operation. You don't want to be running in problems. I would prefer, thinking of cars, I would rather in business say, drive a nice, reliable Toyota Corolla than a fancy, say, Maserati that's going to break every week and I have to go fix it, okay? So that's how you think about it. I don't want to have business executives may tell you, I don't want the greatest, fanciest ML for optimization. Why? Because it works well today, and in 2 weeks, somebody adds a new warehouse or shuts an existing warehouse, and suddenly the machine learning model is producing results that are wacky. That doesn't make sense because it's been so much trained on what we have. So maybe generalizable machine learning model for optimization is the way to go. Maybe there's other ways. Maybe I need to train an ensemble of machine learning models, and then I pick one of them based on how things are unfolding on the ground. Maybe I need these corner case machine learning models, some safety nets to fix the problem before it explodes when I run the model. So that is one big challenge. And of course, there is the big question is how can I a priori know that my machine learning model is no longer valid? Like if I'm going to have this safety net, I need a sort of an alarm that tells me, okay, this new instance looks totally different than what we've seen in the past. Do not run the machine learning model. And of course, if you have that, if you're able to answer that question, then you can answer, okay, how can I patch it? How can I fix my machine learning model and still be able to get reasonable results? So that's, I think, is the #1 challenge really in there. The second challenge is the loss of the quality of results. So when you look at the academic literature, you will see that people are usually obsessed about the constraints. They usually get the solution from the machine learning model and they say, okay, we'll repair it to fix the constraints. Yeah, fair enough. And we're somehow academically trained that constraints are very, very important. And we're going to fix the constraints and we lose 1 and 2 of the quality of results. But in reality, that's not the case. In reality, most of the constraints I've seen are soft constraints. You could violate them and the world is not going to end. Okay, nothing is going to explode. Okay, especially in logistics. So if you are fixing the constraints too much, or your machine learning is whacking them a little bit, then you're gonna go fix it and you lose quality of results. Now think about if you have a business with logistics and it's $100 million operation, and you say, I'm gonna run this machine learning algorithm, it's the greatest technology in optimization, and you're gonna deteriorate your quality of result by 1%, which is $1 million. The answer is just no, I'm not gonna run it, okay? So you have to think about this a little bit in terms of, do you really want to fix your constraints? Maybe don't be obsessed about it. Maybe you don't need to fix it all the way, just a little bit, okay? Because I've seen that's something a lot of people spend on, but in reality, most of the constraints are solved, okay? So be gentle in here. Maybe you want to go for the quality of results. Challenge number 3 is explainability. This is a well-known problem in machine learning, but I think combining it with optimization takes a whole total new dimension. This is actually based on a real case, test case that I've seen. So explainability, okay, in machine learning model, I have this machine learning model. I gave it a picture of a cat. It told me it's a dog. Why did it do that? How did the neural network work? Fine. People are curious about how these things work internally, and it's a fair question. But in here, we're combining it with optimization. So we're generating business decisions, okay? So when you get a wrong business decision, somebody's going to question that and say, why did this business decision happen? So for instance, in here, there was actually a warehouse here in Georgia, and you look at the route that the package has moved through, and it moved to the West Coast and came back to a zip code back in Georgia. Well, some business analyst is going to find this case, and they're going to bring it in a business meeting. Why did this happen? Well, because we deployed the new machine learning algorithm. Then the business director will say, could you explain to me how did this happen? And everybody's silent. We don't know why this machine learning model gave us that result. Well, shut it down and bring the old system. That's going to be the result, okay? People want things that are very, very explainable in business. They think like, they don't trust this machine learning model. And when you're doing image classification, we don't have another exact algorithm that tells us this is a dog or a cat. So people are accepting neural networks because there is no better alternatives, okay? Or no better explainable alternatives. But in here, no. We do have better explainable approaches. Maybe they're not as good, maybe they're not as fast, but they're there. So this is a big problem. And then you could be 99.9% correct all of the time, and just one negative incidence in a few months can shut down a whole system that you build, okay? So this is again, you have to have some kind of safety nets or something that prevents these situations from happening, this extreme, machine learning solutions from happening. Fourth one is planning for scenarios or quantiles. So this is an important. Let's say that planning demand scenarios. You can ask me, what are those demand values that you're giving me that were in the problem? Okay, these were the P50. This is what the expected demand. When you're planning, you want to say, for next week, we're expecting some demand, and you need to hire between 100 and 150 guys to handle that demand. So this means I need to run my optimization solution under different demand scenarios. Okay, so these are totally different problem instances, but the input for them share some physical connection, right? These are different quantiles of demand. Now imagine a machine learning algorithm that's going to generate an approximate solution, and for the 50 percentile quantile demand, it tells you hire 100 guys, but then when you give it the 70% quantile, which is more demand, it tells you hire 95 guys, because it's approximate anyway, right? So you're getting a business decision that doesn't make sense. How can I hire less people when I have more demand? It doesn't make any sense. So in this case, we're not talking just about feasibility within a single problem instance, but you want to have a separate problem instance consistent, the solution with them consistent with each other that obeys this physicality. Okay, so this is something very important too, because we work a lot on fixing the feasibility in a single problem instance rather than a collection of them, okay, which would very well happen. So these are the 4 challenges in here. Sorry, I had to rush, but hopefully and if you're a beginning PhD, you understand some of the big picture directions there and some of the ideas, concrete ideas we looked at in our work, and some of the big challenges in this area. That brings me to the end. Thank you all for coming today. Of course, I acknowledge Abdurrahman Hosni, who's a PhD student of mine. That was his special area. He graduated and now at Apple. I'll take any questions. Any more questions? We had some in the middle. Go ahead.
That is for modeling and optimization problems as well, or
so I think the max set is a nonlinear Is it a linear? It's a nonlinear optimization, so we didn't talk about that. The logic synthesis also is nonlinear, but I didn't have a chance. I rehearsed this talk, believe it or not, but somehow I talked here more than when I rehearsed it by myself. But yeah, some of these problems are nonlinear. Go ahead. Any other questions?
So when you said that most of the constraints are soft, but then you can ignore them and just focus on the quality of the results. At some point, they will have to be fixed, right? So in the real tax system. So do you have in place something that will measure the cost of actually fixing that in practice, right? So because in practice, you will have a number of trucks, or we'll have a specific inventory, and if you violate one of the two, you're going to have a problem. So you have to estimate the cost that came out of the fact that it was not really feasible. So do you have actually a process in place to measure that?
No, not really. So like, yeah, okay. So like we talk about it as soft, right? But soft until what? So this means that you need to repair your solution, but maybe not to be so aggressive in repairing it. Just repair it a little bit, but how much? So maybe it could be 2%, 3%, you know, it's like a soft, like sometimes we even use like goal programming and all of these things, right? And we mark these constraints as soft. So you know, trying to minimize as much as you can the violation, but it's accepted that it's going to be there. So no problem there. So what I'm trying to say is that for some of you say who are doing your research and you're trying to fix the constraint in the solution repair, maybe you don't need to be so aggressive in trying to fix that. Okay, it's okay if you have a violation on it. It's a soft, but don't fix it too much to the point that deteriorates your quality of result much more than it's needed. Maybe you could have deteriorated by 0.5% if you just accept that they're soft. But if you're trying to make it as hard as you can, then you lose it by 2%. And that's where the problem is. People don't want to lose money.
So the other question that I have is that obviously you talk about point forecast, but in practice, you can actually have all kinds of statistical methods that will give you some you know, kind of confidence intervals around that, or some reasonable scenario and so on. Are you actually doing these things in practice, or is just always point forecast?
No, so it's a very excellent question. So the point in here is that we don't do point forecast. We're doing a whole quantile distribution for the demand. So in that case, where did it go? Yeah, in here. Sorry. Oops. This is say that 50 percentile. We're actually having in our machine learning pipeline, it gives you all the different quantiles, the whole distribution, and then you can plan for this distribution. So then the question is, how are we going to marry this with our combinatorial, with our machine learning algorithm that substituted our combinatorial optimization, right? So I give this to my machine learning algorithm, like I was saying, it tells me hire 100 guys here. I give it the P70 percentile. It tells me hire 95.
Yeah, what I was asking is like, are you solving the kind of a robust optimization problem or a stochastic optimization?
We're not, it's a problem. It's a real challenge right now. So it's a problem looking for a solution. Right now we have ways to fix it, like we detect it and say, okay, we have a problem there, but it's a real problem. So think about everything that's been done in stochastic optimization and all of this. Now you want to do it for this machine learning model that you've created instead of the optimization. It's a problem looking for a solution for all the PhD students, smart PhD students here.
Other question.
Go ahead.
So when you talked about the triplet learning at the beginning, you have like different learning steps. Do you do these separately, or can you train the whole thing end to end?
No, we train them end to end. So that's why I actually put that. Yeah, good question. That's why I actually put this figure in here. Yep, this one. So everything is trained together in the triplet sampling, including the parameters in the GCN, including the parameters in the metric learning. You put it in here, you get the final scores, and then you're trying to minimize the loss across the whole stack.
Assertive design with reinforcement learning. What is the reward function?
Yeah, okay. The reward actually is that the neatest and trickiest part in that work. I haven't talked about much, but sorry, but let me show you quickly. So like I said, you have actually two things going on. You have the delay, you have the area for your circuit. So we have this kind of reward engineering table. If your agent action met the delay and improved area, you get a big reward. If it met the timing, but it did not increase the area, you get 0. If you did not meet the timing constraint, but at least you improve the delay, you still get a big reward. If you actually made the timing worse, you get a negative reward. If you made the timing worse and the area worse, you get a big negative reward. So there is this big table that trying to adjust the reward based on how much improvement you're making towards the area and the delay.
At the area, and like, how is the model taking care of like the area and the delay at the same time? Is it adjusted or is it like one single step?
No, it's just one reward number at the end of the day. And, it's as simple as 3, 2, 1, minus 2, minus 3, minus. That's simply the reward.
Okay, this is like
Yeah, because that's the tricky part. Everybody usually does the reward based on the objective function, but this you have the objective and the constraints. So how you combine it? That was the novel part. Good question. Thank you.
Okay, great. We are a little bit over the time, so thank you
Thank you
again.
all for coming. Good luck.